I welcome you all for the session number 8 on interference. Let us discuss about the Newton's rings in this session. Okay, Newton's rings. Newton has observed a circular interference fringes in the light reflected from air film enclosed between the slightly curved surface of a convex lens and a plain glass plate in contact with it, and made a careful study of the diameter of the rings thus formed, and hence they are known as Newton's rings. An arrangement to study Newton's rings is as shown in the figure. Light from a monochromatic source S rendered parallel by a convex lens L1 and reflected by a glass plate G held at 45 degree to the rays. These reflected rays fall on a thin film enclosed by a long focus plano-convex lens L2 and a plain glass plate. The light reflected from the upper and lower surface of the thin air film superimposed on the another to produce the interference rings as shown in the figure. The interference is produced due to the rays reflected from upper and lower surface of the film. If T is the thickness of air film at AA dash, AA1 or BB1, the path difference between the two rays, one reflected from A and other reflected from A1, will be delta x is equal to 2 mu t cos phi. Call it as equation number 1, where phi is the angle of refraction. For air, mu is equal to 1. Since phi is nearly 0, therefore cos phi is equal to 1. Hence, delta x is equal to 2 into mu into t. Since the rays reflected from the upper surface of the air film is reflected from air, that is a rarer medium, and other ray reflected from the lower surface of the air film, that is a denser medium, the second ray experiences further path change of lambda by 2. Due to this, the effective path difference between the interfering rays will be delta x is equal to 2 mu t plus lambda by 2. Therefore, the points A and B lie on the bright ring of a diameter AB is equal to d if the path difference satisfies the following condition: 2 mu t plus lambda by 2 is equal to n lambda. Let us consider a vertical section of ACBE of the plano-convex lens through the center of a curvature of the lens surface as shown in figure 3. Let R be the radius of the curvature of the convex surface of the lens and C be the point of contact of the lens with the glass plate, such that points A and B are equidistant from C. Draw AA1 and BB1 perpendicular to the glass plate P. Let AA1 is equal to BB1 is equal to T be the thickness of the film at the distance R is equal to CA1 is equal to CB1 from the point of contact of the lens with the plate. From the geometry of the circle, we have DE into CD is equal to AD into DB, or CE minus CD into CD is equal to AD square, because AD is equal to DB, or 2R minus T into T is equal to R square, where R is the radius of the ring. Since the radius of curvature capital R of the lens is very large compared to T, we can neglect small t compared to 2R. Therefore, 2RT is equal to R square, which is equal to AB by 2 whole square, which is equal to D by 2 whole square, is equal to D square by 4. Therefore, 2t is equal to d square by 4r, call it as equation number 4, where d is the diameter of the ring. Comparing equations 2 and 4, the diameter of the nth bright ring is given by the following equations: mu into dn squared by 4r is equal to 2n minus 1 into lambda by 2, or dn square is equal to 2n minus 1 into 2 into r into lambda divided by mu, or dn is equal to square root of 2n minus 1 into 2r lambda divided by mu, call it as equation number 5. where n is the integer taking values 1, 2, 3, etc. for first, second and third ring respectively. Since capital R and lambda are the constant, dn is proportional to 2n minus 1 whole to the power of half. Thus, the diameter of the bright rings is proportional to the square root of the odd natural numbers. Also, for the nth dark ring, mu into dn square is equal to 4r is equal to n lambda, or dn square is equal to 4n r lambda by mu, or dn is equal to square root of 4n r lambda divided by mu. Therefore, dn is proportional to square root of n, where n is equal to 1, 2, 3, etc. Thus, the diameter of the dark ring is proportional to the square root of the natural numbers. Okay, let us discuss some questions on the session. The diameter of the bright rings is proportional to square root of dash natural numbers. Option A odd, option B even, option C both A and B, option D none of these. Therefore, the diameter of the bright ring is proportional to the square root of odd natural numbers. Therefore, answer is option A, odd. Second question, the diameter of the dark ring is proportional to the square root of dash natural numbers. Option A odd, option B even, option C both A and B, option D none of the above. The diameter of the dark ring is proportional to the square root of the even natural numbers. Therefore, answer is option B, even. Thank you for patiently listening.